So remember with 2.7, when we're talking about graphing techniques or transformations of functions, it starts with the preliminary understanding of parent graphs. Remember, our parent graphs will be those graphs that we went over previously. The graph of a line, parabola, f of x is equal to x cubed, and the absolute value graphs. So whenever you see when they make reference to the parent graph or y equals f of x, it's actually talking about one of those graphs, either the square root of x, the x squared, x cubed, I think I'm forgetting, an absolute value of x. All right. So the first type of transformation that we're going to talk about, and I'm going to go over all the types as well as how to locate them in a couple problems, but it won't be very many examples for today. All right. But for our first type of transformation is a stretching / shrinking. So starting with the parent graph of y equals f of x, keep in mind this could be the absolute value graph, the square root of x graph, parabola, or y equals x squared, or y equals x cubed. If we're given a function, let's say y is equal to a times f of x, or there's some whole number a in front or multiplying our parent graph, this is going to stretch our graph by a factor of 8. Or the graph will look more skinny. And whenever we're talking about stretching and shrinking, we're referring to it vertically. All right. Where if we're multiplying by a fraction or some number in between 0 and 1, like 1 over a, a good example, it would be something like 3. So if it was 3x squared, that would be an example of the first type. We're multiplying by a whole number 8, and this is going to stretch the graph, or the graph should appear to be skinnier. Where if we had a is 3 here, or we're multiplying by 1/3, for example, like 1/3 x squared, this is going to shrink the graph, or the graph should look flatter. So whenever we're talking about stretching or shrinking, we're talking about it vertically. The way I like to use the way I like to talk to people about it, whenever we say stretch or shrink or multiplying the entire function by either a whole number 8 or a fraction between 0 and 1, like 1 over 3 or 1 over 8, then it's either going to make the graph look skinnier if it's a whole number, flatter or fatter if it's a fraction. Now, technically, and you shouldn't expect too many of these, but we also could do it horizontally. So still starting with that parent graph, y equals f of x. If we were given y is equal to f of ax, this time we're not multiplying the entire parent graph by a number or a fraction, but we're actually multiplying the x in that graph by a number or a fraction. If we're multiplying by a whole number like a, this is going to stretch the graph, or it's going to look longer, because if we're multiplying x by that, either the whole number or the fraction, then it's going to be horizontal. So if we're multiplying by a whole number, it's like we're going to stretch it horizontally, or the graph will look longer. Or if we're multiplying the x by a fraction, like 1 over ax, then it's going to shrink the graph, or it's going to look shorter. All right, so that's our first type of transformation. The next one we're going to talk about is reflecting the graphs. Or it's going to flip over an axis. So the first type of reflection, we're given y is equal to negative f of x. If we're taking the entire function, the parent graph, the square root of x, absolute value of x, x squared, x cubed, just for some examples of some parent graphs. If we're taking the entire function and making it negative, then this flips over the x-axis. Or you can think of it as the graph is upside down. All right, remember, if it's the x-axis, then we're going to flip it. Either top goes to bottom or bottom goes top. Either way, it's going to flip over the x-axis, or we're going to flip it upside down. All right, that's if we're taking the entire parent graph and making it negative. Where if we take the x coordinates in that parent graph, or the x component in the parent graph and make it negative, and it flips over the y-axis. Or it's going to appear to rotate. Or what was on the left is now on the right, and vice versa. What was on the right is now on the left. And the last type of transformation would be a translation. This is either going to be vertical or horizontal. But the first type of translation will be a vertical translation if we're given the function y is equal to f of x plus or minus b. Or if we're taking a number and adding it to our parent graph or subtracting it from our parent graph. It's either going to be up or down b units. So if it's positive, we're going to go up that many units. If it's negative, then we go down that many units. All right, so that's if we're adding or subtracting a number to or from the original parent graph. A good example of that would be something like y is equal to x squared plus 3. That graph is still a parabola. We're just taking that whole every point on that parabola and bumping it up 3 units. Or if we have y is equal to x squared minus 3, still taking that same parabola and just moving every point on that parabola down 3 units. And a good litmus place, or a good place to start would be at the vertex or where the parabola will curve. And if we have a horizontal translation, let's say y is equal to f of x minus c, then we're going to move that either left or right. Let's say right or left. C units. Something else you want to keep in mind, the location of the number. Notice that whether it's B or C, where it's located, if we're adding it to the entire parent graph, vertical shift is either up or down, or if it's attached to X, notice that with this parent graph, it's inside the parentheses with X. Whether we're adding it or subtracting it to or from X, it's going to go right or left. And it's the opposite of what you see, or the opposite of the sign. So if we see X minus C, this means we're going to bump this to the right, C units. Because if you see negative C, or for example, X minus 3, if you see negative 3, you'll think to the left. Horizontal shifts, or those horizontal translations, are the opposite of what you think. Well, the vertical translations are exactly like you would think. So if it's plus B, you go up that many units. If it's minus B, you go down that many units. And by plus and minus, I mean to the entire parent graph. Or if it's horizontal, and we can tell if it's attached to X, either through parentheses, for example, x squared, x cubed will be attached to X through parentheses. Or if it was like absolute value of X, it'll be attached to the absolute value signs. But the horizontal shifts are the ones attached to X, are the opposite of what you see. So if we had X minus 3, you would think negative 3 left 3 units, but because it's a horizontal shift, you go to the opposite of what you would think, or we'll bump it to the right 3 units. Even if it's positive too. So if it was like X plus 3, we'll move that to the left 3 units. Now, the biggest thing is where the number is located, as well as what is it doing to the parent graph. Like I said, if we're adding it to the overall parent graph, vertical, or if it's attached to the X, horizontal. All right. And you'll also notice that like with the stretching and shrinking, where the number is located or what the number is, should I say, a whole number or a fraction is going to affect how we're going to translate the original parent graph. All right. So just try a couple problems so you can see with a few of the translations all in one. And I do suggest that you list all the translations as you see them, just so you can keep up with it. And when I go over a couple problems on the homework, find a problem from the homework, I'll show you what I mean. All right, so we're given the function f of x is equal to negative x minus 1 quantity squared plus 4. Now, where the numbers are, as well as what they're doing to the original parent graph, as well as what is the parent graph, this is going, we're going to graph it. Keep in mind, everybody should have a graphing calculator. So you can use your graphing calculator to check your answers. But I do want you to get in the habit of being able to locate where the number is, as well as what it's going to do to our parent graph. All right, so if we're looking at this problem, the fact that we have x and it's being raised to the second power lets us know that my parent graph should be a parabola. All right, I was going to be referencing the graph of f of x is equal to x squared. So just the fact that it's raised to the second power lets us know that our graph should look like a U. Now, whether that U is facing up, facing down, shifted left, right, or rotated about the axes, as well as stretched or shrunk, is really going to be told to us by where the numbers are, what the numbers are doing, and where the signs are located in the problem. All right. So this little negative sign out front, this takes the entire function and makes it negative. So we're not taking the x's and making it negative. We're taking the entire f of x and making it negative. So this lets us know that it's going to flip over the x-axis. I'm going to just write this down here as well so we can keep up with everything. All right. Now that negative was inside attached to the x, or inside the parentheses for this particular example, that will flip about the y. But because it's in front, it's taking the entire parent graph, or f of x, and making it negative, that flips over the x-axis. So typically the parabola will open up, but because it is negative sign, it's not going to open down. We have this -1 inside parentheses attached to the x. That's going to be a horizontal shift or horizontal translation. Keep in mind that goes the opposite of what we would think. So we see -1. This is going to have to be bumped to the right 1 unit. We also see that we're adding a +4 to that overall parent graph. Remember, if we're adding or subtracting a number to or from, that's a vertical translation. Vertical translations go exactly like we would think. So this will go up 4 units. Now, because we're dealing with parabola, I would suggest that whenever we're moving it left, right, up, or down, we really want to focus on the vertex. All right. So this is my parent graph of a parabola going through the origin. This is what we're going to start with. And then we're going to use these translations to graph this particular function. All right. So starting with the vertex here, I know I'm going to move it to the right 1 unit. And I'm going to move it up 4 units. So what was at the order pair 0, 0 is now going to be at the order pair 1, 4. We also want to remember that we're going to have to flip this parabola over because it rotates or it reflects about the x-axis. All right. So the vertex of this new parabola at the order pair 1, 4, I'm going to bump it to the right 1, up 4 units. That handles these two translations. And I'm going to make sure that parabola opens down because it reflects over the x-axis. So this would be the graph of the function f of x which is negative x minus 1 quantity squared plus 4. And if you have a graphing calculator, what you could do is simply plug in, and that first slot y1 is equal to a negative, open parentheses, x minus 1 squared plus 4, and you should get the same exact graph. So those graphing calculators are a very good tool for you to check what you think, or what it is to check what you expect in the problem, given your translation. Also a good way to see if you forgot one. Like if you remember to bump to the right one and up 4, but you forgot to flip it over, when you graph this function, you'll see that that parabola opens down while your graph opens up. So it's a very good way of checking yourself. Are there any questions on this first example? All right, so if we're given the function f of x, which is equal to negative 2 times the absolute value of x plus 3. All right, so once again, we have that negative sign out front. Well, first off, my parent graph is the absolute value sum. Hence, we have absolute value in the actual problem. So our graph is going to look like a V. Remember, that's one of those few graphs that I said that we need to know like the back of our hand. All right, but we have a negative sign out front. Notice that the negative sign is not attached to any x's inside the absolute value symbol. So this is going to reflect over the x-axis. So we can say that this V flips over x-axis. We also have a number in front multiplying the parent graph by 2. So this is going to affect our stretching and our shrinking, keeping in mind that if it's a whole number greater than 1, then it's going to stretch by a factor, in this case of 2. Where if it was a fraction, let's say if it had been 1/2, it would shrink by a factor of 1/2. But because this is a whole number, it's going to stretch by a factor of 2. Our overall graph should look skinnier. And we also have a horizontal shift. Remember this positive 3 inside the absolute value bars, or it's attached to x through those absolute value bars. Horizontal shifts go the opposite of what we think. So we see positive 3 plus 3 on the number line will be to the right 3 units. But because it's a horizontal shift, we're going to have to move it to the left 3 units. All right. So this is actually going to be the graph that we start with. This dotted line, should I say? The absolute value graph going right through the origin. This is before we have apply any of the transformations. Now we know that this graph is going to have to flip over the x-axis, or if it was opening up, our new graph should be opening down. It should be stretched by a factor of 2. And that whole stretch by a factor of 2, it's not going to be a real big deal for us. Now, the factor of 2 part is going to be important when you're doing the homework, because it's going to be a part, or at least a segment of each problem where you can plug in the stretching factor or shrinking factor. And if you type in 2, the computer will handle that stretching and shrinking for you. Now, you do need to know the difference between whether it stretches or shrinks. And you can tell that by being a whole number, which means it will stretch, or if it was a fraction, it would shrink. But overall, the graph should be skinnier. Outside of that, we have to shift the whole graph to the left 3 units. So what was at the order pair 0, 0, our origin, is now going to be at the order pair -3, 0. Keeping in mind that the V should flip over, and it should be visually skinnier. All right. So this should be the graph of the function that we're looking for, more specifically, the function -2 times the absolute value of x plus 3. All right. Any questions on this example?
This has to be like a little bit skinnier, or does it have to be exact?
It does have to be exact. Remember on the test is only multiple choice, so you just got to pick the one that's going to look that way. And then in homework, you're going to actually plug it in, the 2 or the 1/2, just for a quick example, and then the computer will handle that part for you. Any other questions though? All right. One more for this final problem for the homework. Say we're given f of x is equal to 1/2 times the square root of x plus 2, which is underneath our radical, minus 3, which is not underneath our radical. Right. So here our parent graph will be that radical or the square root symbol. I believe in the previous examples, when I first introduced it to you, I called it a shooting star. At least that's what where they reference it. The graph that we're going to start with starts at the origin. It should look like so. Now this time we'll multiply the entire parent graph by 1/2. So instead of stretching, it's going to shrink by a factor of 1/2. We have a horizontal component. We know it's a horizontal component, positive 2, is because it's attached to the x through that square root symbol. So this positive 2 underneath our radical, that's how we attach to x. This is how we know that it's a horizontal shift. Horizontal shifts go the opposite of what we think. We see positive 2, so this means we're going to have to shift it to the left 2 units. We also have a vertical component. We know it's a vertical component because it's being added to or subtracted from the parent graph or off to the end. Vertical shifts go exactly like we would think. We see -3, so we're going to shift it down 3 units. All right, so what are, for our parent graph, we started at the origin 0, 0. We know we have to go to the left 2, down 3. So it was at the origin is now at the order pair -2, 3. We already know that it should be the shooting star graph, so the graph should look like so, but it needs to shrink by a factor of 1/2. Now, whenever we're talking about shrinking, we mean vertically. So it should look flatter. Keep in mind on the homework, on the homework and on the test, you need to be able to visually see if it's flatter or comparing to our original parent graph, is it flatter or skinnier? And in the homework, the fact that you can type in the shrink by a factor of 1/2, it'll handle that for you. All right? So we can see the location of the number as well as what the number is doing to the overall function is going to tell us what type of translation we have. By that, I mean reflecting about the x-axis, the y-axis. Remember, if it's reflecting, that's that negative symbol. If it's out front, it's the x-axis. If it's attached to the x, it's the y-axis. The stretching and shrinking, if we're multiplying by a whole number or a number greater than 1 or a fraction, a number between 0 and 1, that's going to tell us if it stretches or shrinks respectively, as well as our parent graphs. Keep in mind, our parent graphs, absolute value of x, square root of x, x squared, x cubed, y equals x. These are the graphs that we're going to be transforming in these problems. All right. Any questions on this example? All right, so I'm going to try. All right, so we want to final problem where we actually get to practice the graphing as far as the homework goes and make sure we're not making any mistakes on something small. All right, so with this problem, we're asked to graph the following function and we're given the function g of x which is equal to x minus, or the absolute value of x minus 4. All right, I know that's difficult for you to see in the problem, but hopefully you can see a little better on the graph. But just for the sake of the ones who are, we'll go back and watch the video. This is the function we have. G of x is equal to the absolute value of x minus 4. So before we actually go back and graph it, we can see that the only translation we have is a vertical one. That -4 is being subtracted from the absolute value of x. All right, so then we know we're going to have to bump this down 4 units. All right. So on the homework, we want to get ready to handle a problem like this. We want to go click to enlarge the graph. And off to the right, you can see that they give us a few of these parent graphs. We have a parabola, we have the absolute value, we have a line, and we can actually type in a few things if we wanted to. Now, because they already know that this is the absolute value graph, what I would suggest we do, click on the absolute value here. And because it's going to be bumped down 4 units, I'm actually going to go down to -4 on the y-axis to handle that translation. Now, with the absolute value, we have to type in our slope. This is where we can handle that factor of 2, factor of 1, or a factor of 1/2. Because this is just the absolute value of x, this has a regular slope or a slope of 1. So from this point at -4, or excuse me, 0, -4, we can just go up 1, up 1 to the right 1. And that's our standard absolute value graph. All right, we can click save. This is the graph that we want to check. And of course, we can check our answer and let us know if we got the right answer or not. All right, so it's going to give you some options as far as the stretching, shrinking, reflecting, horizontal shifts, or vertical shifts. I want to see if I can find another one. It's a little better. All right, so here it says graph the following function. This time we have g of x is equal to x plus 10 quantity squared. That's for the ones who watch on up here. All right, so this is the one that we're going to be graphing, x plus 10 quantity squared. This has a horizontal shift of 10. We can tell because it's attached to the x, it's inside our parentheses. We're going to be starting with parabola. And we can tell this because its power is 2. And it has a horizontal shift, so we're going to bump it to the left 10 units. Remember, horizontal shifts are the opposite of what we see, or opposite of what we see. We see positive 10 means we have to go to the right 10 units. This is when we remember it's a horizontal shift, so we have to go to the left 10 units. All right, so we can click here and enlarge the graph. We have a parabola. Notice how the functions or the options have changed a little bit. We have parabola and the x cubed as our options. I'm going to click on our parabola. So we click on the x squared tool. We're going to bump this to the left 10 units. So we're going to go to the left over to -10. Make sure we stand on the x-axis. That's -8, -9, -10 would be here. Now, see, when I clicked on it, it put it right there in the origin for us. Notice that in this box off to the left, or excuse me, off to the right on the screen, we have a vertical stretch, horizontal stretch, vertical shift, horizontal shift, as well as clicking on the X reflection or the Y reflection. So it gives us a lot of options as far as plugging it in. This is why I suggest that if you have those options or an original problem, write down all your transformations, because it does not matter the order in which you plug them in, but it does matter that you account for all of them. So here we only have a horizontal shift, horizontal shift. So we're going to keep the vertical stretch and the horizontal stretch at 1, because that means it's going to stay as our parent graph. With a horizontal shift, we're going to bump it. Now, notice that when I plugged in 10, even though we see positive 10, it moved. And by it, I mean the graph of the parabola moved to the right 10. Now, because it's a horizontal shift, we know it's the opposite of what we see. So we're not going to plug in 10. We're actually going to have to plug in -10 to make sure that it goes the right way. So it accounts for it, you can save it, and obviously check our answer. All right. So whenever you're working on the homework, it's going to give you a few options. You're going to have to play with it a little bit, especially if you have never worked with this type of with this software. But the transformations and what we went over should apply. Okay? Are any questions on what we're doing with the homework? Any questions on this section? All right. Once again, my plan to have a test 1 week from Wednesday. So I'm probably going to tell you again, next time we meet, the test is in a week. So we're going to finish 2-8 on Wednesday, probably put up the review for Monday of next week, at least before Monday of next week, so you can have a chance to go over it, come bring in, come ask your questions if you have any. Test will be Wednesday. If you don't have any questions, you guys are free to go, and I'll see you on Wednesday this week. Good luck studying.